welcome to the second video on recursion, and we're going to try to get you to think recursively. I know it's a new topic and people get all nervous about recursion, but it's just another thing that you have to wrap your mind around. And one of the reasons you study recursion is you say, well, why do we have to go through this technique? It turns out there's a lot of algorithms, and especially when you talk, when we do trees, that are represented recursively with a lot less code than iterative techniques. Okay, you're going to have to take my word for it. What could take a page of code can literally just be done recursively in 5 lines. But you have to understand why, how recursion works, and so we're going to give you more and more examples to have your mind wrapped around recursion. The next example I'm going to talk about is greatest common divisor. Okay, now, if I give you the greatest common divisor, say I would like to find the biggest number that goes into those first two numbers, 48 and 36. So in other words, if I come down here, let's see what that is. The greatest common divisor, iterative. Let's just do iterative. And we pass it 48 and 36. Okay, what should come out? What's the biggest number goes into 48 and 36? 12. There you go. Now, how do you do that? Well, it's not a hard thing to do, to understand that this is a series of numbers that get generated. This is called Euler's technique. And Euler figured out that take these two numbers, okay, and you have to use the absolute values of those numbers, otherwise it doesn't really work too well, okay? And so what happens is, as long as the second number is not 0, the next number in the series is going to be 48 mod 36 to give you 12, okay? Once we get that mod value, we're going to do another iteration where we're going to make m equal to 36, n equal to 12, okay, m's equal to 36, n's equal to 12, so that we go ahead and do another iteration. Now, so picture m is 48, n is 36, that generates a 12, so these two numbers are essentially done. Now what I want to do is another iteration where this 36 becomes m, so n is equal to m, 12 is the mod that we calculated, the next value inside the series, n is 12, so look at those two values, okay? Well, n being 12 is not equal to 0, so the next iteration is the mod. 12 goes into 36 3 times, but with a remainder of 0. It's that remainder that you use to generate the series of numbers. Okay, now these two numbers have done its job. Now what we want to do is look at these two numbers, and in order to do that, we need to switch these values around. N becomes 12. N becomes the 0 we calculated. Because n is now 0, we stop this while loop, and the value just before the 0 is the greatest common factor. That's a beautiful algorithm, Euler's algorithm. Now we could do this recursively using this technique. Look at this. This technique actually is fairly, where did it go? Actually, this technique needs to have a helper function to start off, because where's the absolute values here? Okay, pretend this private method is not available to the user, but there is a public method, public, to start off that the user can call, public static integer greatest common divisor. We'll pass it m and integer m and integer n. Okay, now there's going to be an error there because these methods have the same signature. Let me call this the helper. Helper. Okay, the helper function is hidden from the user. The user sees this right here. So in order to get this to work properly, I need to make sure or sanitize the values before the helper function actually does its job. So what I'm going to do is say, well, let's call the helper function GCD, and what I'm going to do is make sure that we use the absolute value of m and pass it the math.absolute value of n, and make sure that, so in other words, the helper function is going to get two positive values, and we're just going to rely on that helper function to return the proper value. Let's return it. Okay, so let's put a semicolon in there, and it should be nice and ready to work. Okay, so we have this helper function. So pretend that the user doesn't see this helper function. They just see this. And all we're doing with this public method is to start the recursion with valid values. Now let's take a look at this. All right. Just like we saw here, all we care about are the last two values in the sequence. As we build the sequence, we're just looking at the last two values, where this is m and n, then the next iteration m and n. And what we're saying is, if n is equal to 0, there's nothing to calculate. Just return this parameter here. Okay? But if n is, like, say we have 48 and 36. m is 48, this is 36. Okay, now look what we're doing here. We're calling the helper function. We're taking that 36 that was n, passing it as the first parameter, and when we pass it as the first parameter, it becomes m in the next iteration. And then the n becomes 48 mod 36, which is the 12. So this generates this. So in the next iteration, m and n are those values there. So here's what I got. You can see it from these values. If I passed it GCD, pretend I said GCD helper, GCD 48 and 36, well, what happens is I need to call the helper function with the values 36 and 12. That's what we're doing here. Well, that doesn't mean any base cases. There's no zeros here. So that in order to calculate this guy here, I need to call GCD again, pass the 12 as the first parameter, 36 mod 12 is 0, call it again, GCD, mn, 12 and 0, hey listen, n is equal to 0, and just return the 12, the first parameter. And what I'm describing here is what the book calls tail recursion. Tail recursion builds the answer as you go down with each stack call, each frame that you call, each invocation of GCD. You're building the answer. And once you get that answer, you just return it back to each level and return that back. Right? That's called tail recursion. I'm going to give you more examples of tail recursion. But you could see that, let's see, GCD helper, GCD, let's see if GCD works. I did some serious work there, GCD, pass it, we should see 12, and it worked great. All right. And just one more example. How about an example that deals with powers? Okay. What I would like to do is say, I know there's a power function inside the math.library. Power, say we would like 3 raised to the 5th power. Okay. How do we do this? Well, first off, how come there's an error there? There's always errors. Oh. I see. 3.0. Okay, now why is that? Oh, I see, double. See, the way this was written is that this is supposed to return a double. So you can see that the power 3.0 raised to the 5th power is 3 times 3 times 3 times 3 times 3, 5 times. And because I wanted to return a double, because an integer would overflow really quickly when you do powers. How do you do it? Now, you can certainly do that iteratively. Let's do it recursively by coming up here, take a look at it. I don't think we need any helper functions to start the process off. So in this case, the base of the power is 3.0, exponent is 5. And here's the way I would approach it. Let's pretend we don't see this. Pretend we don't see that part there. If the exponent is equal to 0, basically there's nothing to calculate. It's base raised to the 0 power, and we know that to be 1. That's your base case. Now, that was not too interesting. Say what we wanted is 3 to the 5th power. Base is 3, exponent is 5. See, well, what we're going to do is say, well, the base really doesn't change in each level of recursion. It's just that the power function gets called with the same base. Instead of 5, return it 4. See, so 3 to the... So basically what we're saying mathematically is that 3.0 raised to the 5th power is equal to, let's comment this out, okay, is equal to, well, that's too complicated. It's equal to 3.0 times 3.0 raised to the 4th power. I don't think you're going to argue with that. You're masters of math. You're taking calculus and all that fancy math. So this, basically, each time we do this, what you have to assume is that, hey, if I were to pass at 3.0 and this 4, what comes back is the proper value of 3 to the 4th power. All I need to do is take that number, multiply it by the base 3, and that's 3 to the 5th power. That's it. That's great. And so we can even do negative powers by simply doing this. So you ask the question, what is 3 to the, what is, let me say that. What's 3.0 raised to the minus 5? Well, you know that that's basically, remember the rules of exponents, 1 divided by 3.0 raised to the positive exponent. So all we're going to do is say, well, if the exponent's negative, literally do your math. 1.0 divided by power raised to the negative exponent. So negative and negative is positive, so what you're going to be doing is calculating the same function is going to return 3 to the positive 5. That's going to be, that value comes back, you're dividing it into 1.0, and you get the answer. I mean, this is beautiful. We're not using any loops. You are using stack frames, but that's okay. That's okay. Let's see if this works. 3 to the 5th. Let's see what happens here. Okay, 3 to the 5th, that looks about right. And if I say 3 to the negative 5, yeah, all right. Okay, I'll take their word for it. I believe that's correct. And 3 to the 0 is 1. Perfect. That works great. So what I'm going to do here is stop the video, let you digest what we just did, and of course you have the source code available to you. Why don't we just let you take a look at what we did, and I'll give you more examples. All right, bye.